one of the real powers of vector valued functions is that we can extend them to higher dimensions really easily, even though we can't visualize them graphically because we are at our mental capacity as humans thinking of everything in 2 and 3 dimensions. But mathematically, it would all work past 3 dimensions into 5, 6, 7 dimensions. Who knows? All right, so we're going to concentrate, of course, on 2 and 3 dimensions because that's the limit of our human capacity to visualize. And the first thing we want to look at is linear functions. So linear functions are going to be a very common thing that we're going to have to work with in this course. So it'll be important for us to know how to take what used to be just a line in algebra class and expand it into a vector valued form of that line. All right, so we're going to start with the equation y equals 2x minus 3. All right, so we know what that looks like. It has -3 as its y-intercept. Well, 0, -3. And the rise over the run is 2 over 1. Let me grab a ruler. Try to be good on this one. Instead of just drawing it by hand. There we have it. And it doesn't have any restrictions, so I'm just kind of putting arrows on it because it had no restrictions on its domain that we can tell. Okay, so we want to find the vector value form of that equation. So if we wrote it in parametric form as kind of a way station, we would let x be t, we'd let y be 2t minus 3, and our domain would actually be from -infinity to infinity. I didn't mean to have an extra line in there, just kind of. All right, so that would mean that r of t would be t comma 2t minus 3. Now, this is correct, but it's not the most common way that we write it, or it is one of the common ways we write it, but there's another way as well. And that is to break off the t components and the number components into 2 separate vectors that are added. So if this was the case, that would mean that r of t is also equal to the vector t 2t plus the vector, well, there's no numerical component here, so 0, -3. And then we can also go one step further and factor, if you will, the t out of here and say, look, that's t times the coefficient of the t here was 1. The coefficient of the t here is 2 plus 0, -3. And this is a very common way for us to write a linear equation in a vector valued form. The other two are also correct. It's just that this one was the one we were shooting for. Right. So let's look at it. Why do we like it in this form? What value does it have? Well, because this particular piece right here, I don't know if you caught it when I was doing this. What did I say? Up 2 over 1, up 2 over 1. It has a rise of 2 and a run of 1. Rise of 2, the vertical component, run of 1, right? It's your direction vector. It's telling you what direction you're going. It's the equivalent of the slope from algebra. Right? It's just written in a different way. We would say the run is here and the rise is here. Right? But that's what you're looking at. Right? And then what about this component? Well, it's the vector form of your y-intercept, right? Your starting point. Because 0, -3 would be the vector pointing to that point. So if you will, it's your starting point. Now, in algebra class, that was always a y-intercept. That will not always be the case because it will not always be on the x-axis. So I don't want to say that it's the y-intercept because it's not. We're taking the ideas from algebra and expanding on them. So in algebra, it was the y-intercept that we always used as our starting point when we put it into this form. But of course, that will not be the case in this case. It'll just be any point where it could work. But you get the idea. Oh, so I did this piece where I rewrote it. So, if you will, this piece is up here, and this rewriting the equation was right there. Sorry. So I was just getting ahead of myself. So there's the terms with the parameter, right? Here's the term with the parameter. That's the parameter t. And there's the piece without the parameter. All right, so now that we understand how this works, we can expand that to the equation of a line in 3 space. It'll work the same way. So we have a vector v, and it has a direction vector, and then for a line that is parallel to the line. The equation of a line containing point P with direction vector v is, and what we just saw, t times the direction vector v, which is the new and improved way of thinking about slope, right? But it's not slope, it's direction, right? Slope always was direction, right? It's kind of expanding that idea. And then O stands for the origin. So this is the point from the origin. So OP is from the origin to point P, right? O stands for origin. Right? It's a vector from the origin to that point. Well, and that gives us these forms, right? So we have direction vector AB, right? So if you had a 2-dimensional vector, you'd have a 2-dimensional point and it would work, or you could do a 3-dimensional, right? But either way, this is the big one, right? We're going to use this a lot. Okay, so let's find 4 different vector equations for the line PQ given point P, which is 2, 3, and Q, which is -1, 5. Okay, so let me start by finding the direction vector from P to Q. So let me do that. Now remember, for that we do terminal minus initial. So Q would be -1, that's the terminal, minus P, and then 5 take away 3 would get me -3, 2. And I just really quickly kind of drew a little sketch here. So we have a line that actually contains these 2 points, right? So I have 2, 3 over here, and I have -1, 5. So what I just did was I found the direction from P to Q. So from P to Q, it would go that way. So it's pointing that direction, -3, 2, right? So x -2. So then I just need a point, right? So this is a direction vector, right? What we just found. This is a direction vector. And it's pointing that way, right? It's pointing -3, 2. If you want to think of it that way. Vectors are free. I can draw it like that. Okay, so now I can use that direction vector, and I can come up with the vector value form equation for this particular line 2 ways. One by using point P, and right, because I would start at P and go that way. One by using point Q and start Q and go that way. They both work because vectors are free, right? Okay, so let's use point P. Using P, you would say R of t equals t times your direction vector, which is -3, 2, plus, and I'm going to make point P become a vector by going from the origin. So it'll be 2, 3. There it is. Now, a lot of times we don't leave it in that form because it's just awkward. So we also write it as -3t plus 2, 2t plus 3. So that is also correct. All right, so now let's keep using that direction vector, but let's use Q, right? So I basically just found this one. Start at P and go that direction. But I could also start at Q and go that direction. That is still on that line, right? So here, let me color code these. So that's the first one I found, the green one. And I'm going to do this in pink or something. So it's going to start at Q and go that same direction because the direction vector is the same. So it's pointing that way. All right, so then R of t would be equal to t times that same direction vector, -3, 2, plus q, which would be -1, 5. Again, that's kind of awkward to write it that way, so a lot of times we don't. I'm just going to write it another way right over here. I don't want to run out of room. -3t minus 1, and then 2t plus 5 would also be correct. They both work as ways to write this. Okay, but it said to do this 4 times, and so far we only have 2 of them. We have starting at P and going that way, and we have starting at Q and going that same direction. But what's the other direction? Well, it's pointing downward, right? It's working your way down the line. So instead of going PQ, my second direction vector could be QP, right? So direction vector number 2 would be QP, and we already know what that would be. It's 3, -2, right? Because it's going the opposite way, right? So the signs just switch. And if you want to, double check me, but it's going to work, QP. All right, so then if I'm going to use point P, let me grab here, using P, point P, and that new direction vector, I would say R of t equals t times 3, -2 plus 2, 3. Sorry, I didn't color code that. There you go, just so you can see it's that new direction vector getting used. And then again, this is perfectly fine, but we often change it up to write it 3t plus 2, -2t plus 3. So what happened? I started at P, and I'm actually going the other way, right? I didn't want to draw it on the line because it's getting confusing, but it's that way, right? That's what I'm doing. All right, well, I could start at Q and do the same thing, right? They're all on the line, right? So if I use Q, right, that would go start at Q and go that way, right? So it would be R of t equals t times 3, -2 plus -1, 5, which would be 3t take away 1, -2t plus 5. All right, so example 5, how could I modify those answers to just get the line segment? And the answer is you just need to restrict your domain, right? So if you restrict your domain, you can get just from P to Q. Now you can only do it for a couple of them. So let's think. It has to be the ones that are in here, right? The pink one that starts at Q and goes that direction won't work because that's going the wrong way. And the P one that starts here and goes that direction is not going to work, right? So this pink one and this light green one aren't going to work. So these two would be out. But this other one, the first one we found and the last one we found would actually work. One starts at P and goes that way. So that would work. And one starts at Q and goes the opposite way. So let's look at the first one. So we would go R of t equals, it was -3t plus 2, 2t plus 3. And we'd want to restrict ourselves so that we were going from point P. So let's look at what point P looks like. P is 2, 3. Okay, so think about that. If this was the case, if -3t plus 2 was equal to 2, because that's the x component, that would mean that negative 3t is 0, so t is 0. So we'd want to restrict ourselves from 0 to q, which is negative 1, 5. So we would set negative 3t plus 2 equal to negative 1, and we would solve that. So negative 3t equals negative 3, t equals 1. So this particular one would go from, if we're trying to go from p to q, we would say 0 is less than or equal to t, which is less than or equal to 1. All right, what if we did it for the blue one? Okay, so then r of t would be equal to 3t take away 1, negative 2t plus 5. And then we'd have to do this whole PQ thing over again, right? Because it's different. So if P is, so I'm just trying to think here. I'm just going to segment that off. Okay, so now I would need 3t minus 1 to be equal to 2, right? Because the x component would have to be equal to x component for that point. All right, so that would be add 1, so 3t equals 3, so t equals 1. And then over here, I would say negative 2t plus 5 equals 5. So subtract 5, negative 2t equals 0. Oh, look at that, t is 0. So again, we would be restricting ourselves from 0 to 1. Now I lied a little bit. We actually could do the pink one and the green one, but we'd have to remember that the vector is free and kind of shove it. So you could do this, but you'd have to restrict your domain in a weird way. So you'd take this vector in direction that it is, and then you'd move it by letting your t be a negative value. Right? So you could even do it with the pink one. Let me show you how. So if I wanted to do this one, I would say, I'm running out of space here. To do the point P, which is 2, I'd have to let me sneak it in right here. Negative 3t minus 1 equals 2, right? So when you add 1, you get 3, and so negative 3t equals 3, so t equals negative 1. So it'd be from negative 1, which is less than or equal to t, and then if you do this over here, you're going to get 0. So it can work even with the pink one. It's just not intuitive, perhaps. But you could do it with the pink one, it'd be negative. And the green one's the same way. It'll end up being a negative t value. So all of them can work if you restrict your domain enough. So there it is for the green one too. And I should add, sometimes I'm only showing, I showed P and I showed Q. I can do X to both. I can do X, I could do a Y. Like, you can do X for both and then Y for both. You know, you should be able to get your domain restrictions one way or the other. So for this particular one, for the pink one, I just know where this is going, so I put it in. But you can set your X component equal to the X component for the 2 points. You could set your Y component equal. So sorry, I did the Y component here, but the X component there, it's fine. I mean, it's going to work out. So I'll be able to find the 2 values. So sometimes you do just X and X, sometimes you can do Y and Y. As long as you can find the 2 particular values for your domain, that's all that you need to do.